without further ado, let us give the word to Paul Winter. Of course, he's one of our members and at the same time affiliated to Princeton University. And he's going to talk about regularity for minimal surfaces in the context of geometric measure theory and outlook and recent progress. Yes.
So, yeah, okay. So yeah, my talk is very much going to be like, okay, there's quite a lot of people in the audience that know geometric measure theory, but I was planning on going quite slow and just talking about maybe different relations between this stuff and other geometric problems, which recently I've been getting sort of excited by. So I prepared the talk sort of being excited by these things, and I'm not necessarily an expert at everything I'm going to talk about, but like, so, but hopefully still I can give some ideas of where some interesting things are potentially happening and going on. So yeah, so this is going to be like an overview. It's a very generic title. An overview of geometric measure theory, specifically area minimizers and recent work. That recent work being with Camillo and Anna, who are both here. So, okay, we're not going to get to the recent work really until the very end. So I wanted to start with more of an overview of types of problems which are still present and where these things appear. So, okay, what is the, very broadly speaking, what is the aim of what we're trying to do? We're trying to do geometry. We're trying to understand the relation between geometry and topology. So, understand relation between geometry and topology. So, how geometry influences topology and how topology influences geometry. And so one of the first instances that everyone sees of this is, say, the Gauss-Bonnet theorem, which tells you if you integrate the Gauss curvature over a surface, you're going to get some multiple of the Euler characteristic, which gives you simple consequences like you can't have some deformation of a torus which has a positive Gauss curvature because the Euler characteristic vanishes. So yeah, this is what the sort of broadly what we're interested in, and so the issue with all of this is that there's no, maybe arguably it's very hard to find a canonical way to view geometry. The same topological object can geometrically look very different. You just put a different metric and things can be so it's very different. So there's this sort of arbitrariness in geometry, where you could look at S2 in sort of the usual way. If I asked you to picture S2, you'd most likely think of something like this. But topologically, there are other objects which topologically are the same, but have very sort of different geometries. And the whole issue of the sort of issue that this creates is, well, if I give you a geometric object and ask you to understand it, how do you go about doing that? I mean, somehow the geometry has to tell you something, or you'd hope the geometry tells you something. But because there's all this sort of degeneracy, how do you pick out the useful information? So, so there are numerous ways which people attempt or approach this problem. One of the popular ways nowadays is, I guess, trying to find good metrics on a given manifold. And so, one of the ways of doing this is using geometric flows. So Ricci flow is very popular nowadays. But then there are other sort of geometric flows like the curvature flow, the Yamabe flow, all of which are kind of like, the aim is to somehow move from some sort of arbitrary picture to some more canonical picture where you have geometry which you can then use to study the manifold. So ideally you want some sort of, so maybe the question is how to get a handle on geometry in light of this arbitrariness. And yet one way is by finding good metrics on your manifold. So everything I talk about is smooth. So you have Riemannian metrics, and some metrics are better than others. Like in this picture, like this is the picture you will always imagine. This is what you imagine. Okay, so that's very broadly, this is very sort of slow, if you will, sort of what we're interested in. And so once you've maybe found a good metric or something in your manifold, how do you then use that metric and the properties of that metric to understand global properties of the manifold? And one way of doing this is by utilizing certain special substructures of the manifold or special submanifolds or things related to the manifold in some way. So you somehow attach a special object to the manifold, and the existence of such an object can tell you how to probe the manifold itself. So yeah, let's just say once you have a good metric, whatever that means, depending on the problem, one way of progressing is to find special substructures whose existence and properties somehow reflect the ambient geometry. So whose properties somehow reflect the ambient geometry. And so typically, at least in the things I know about, these special substructures or special submanifolds, say, are solutions to some sort of geometric variational problem, which means they're sort of, there's a PDE, you could think about it this way, there's some sort of PDE and this is on the manifold and it's a solution to the PDE. So, and this is typically how maybe things come about. So let's just say typically, these are solutions to geometric variation problems. Which you could think of as satisfying PDE. Now, okay, just as a sort of hint towards we're going, like this corresponding to satisfying a PDE is not exactly like necessarily true in every case, because just like when you're looking at functions, often to actually some of your solutions to sort of regular PDE are not solutions in the sense of a smooth function. You have these sort of weak notions of solution, and so they don't solve the PDE in the usual way. So similarly here, like the solution to the geometric variational problem, if you have enough regularity, then you can write down some PDE which is going to solve. But in general, like maybe not that it actually solves a PDE because you haven't got enough regularity to talk about derivatives, etc. at that moment in time. Okay. So this is a very broad picture. So I wanted to then give quite a few examples of varying sort of levels of where such special structures come up and how, what sort of things you can prove using these structures. Any questions so far? This is very vague, maybe, but like. So okay, the first example is something that everyone's going to be familiar with. This is just the idea of a geodesic. So this fits into this framework because a geodesic is, locally, a geodesic is length minimizing. So it has this variational structure. In this case, you have additional regularity as well, but let's forget about that for a second. So this is locally length minimizing. So you have 2 points in your manifold, some path between them, and if you look locally about any point, it's minimizing the length in that region. Okay, so this is, you open a Topology, you flick through it, and you find a section of variational problems, and then you find some applications of using geodesics and geometry. So let me just recall a few. Two. So, for example, you have the Minimise theorem. So this tells you that if you have a complete manifold, it's complete, and you have some uniform Ricci lower bound, 1/r squared, then actually you get this global topological conclusion that M has to be compact. You have a diameter bound in this metric, something in terms of the Ricci lower bound you have, and moreover that actually you have this, this is a topological consequence, but you also get that the fundamental group is finite. So this is an example of how somehow you have this manifold with some geometric condition, also the metric. You find some special structure, and then you utilize properties of that special structure to then prove topological conclusions for the ambient manifold. Another example, using geodesics, again, just from Topology, is the Singe theorem, which, let me just write this down. So you have the same sort of setup, you have a compact manifold, and now you assume some sectional curvature bound, just not negative. Negative sectional curvature, and then you get conclusions depending on the dimensions. So then if n is even and m is orientable, then actually n has to be simply connected. And if n is odd, then actually m has to be oriented. Okay, so what I'm trying to illustrate is that, you can use these special structures, which in this case are just one-dimensional manifolds, to control somehow the ambient geometry. And in this case, the reason this comes up is because if you have something which is locally length minimizing, this means one, it's a critical point of area, and also the second variation of area is non-negative, because you can only increase area or length. And so when you write down the formulas you get from those two, you can do the computation, and you find out that actually for the second variation, there in the formula there's some curvature terms about. And so somehow you can utilize this presence of the curvature terms appearing in the second variation of length to then get these topological conclusions. And so maybe I should just remark that, so as another sort of consequence of the first one, because pi1 is finite, that means if you take any manifold, you cross it with S1, that's going to have infinite fundamental group. And so therefore, it can't exhibit a metric which has a uniform Ricci lower bound like this. So, these special structures are giving you information. Okay, continuing my list of why we should be interested in these things. So my second example is going to be taking the geodesic is a one-dimensional object which satisfies this sort of length, the area criticality. If you up the dimension, then you're looking at, say, surfaces. And often actually the most useful, like one of the easiest sort of dimensions of a sort of surface to study, which is maybe critical for area, is the opposite to length. Length is one-dimensional, so go for codimension 1, the other side. So these would be minimal hypersurfaces, let's say, which are, say, you could say area minimizing, but even just being stable. So being a non-negative second variation again. Just like over here, the main thing we used of the locally and area length minimizing was the second variation. So yeah, these are critical points of now area, codimension 1 area, which you can formalize using Hausdorff measure. And they have non-negative second variation. So this is this first variation of area is equal to 0. This is second variation, non-negative. And so, okay, examples of things which you can prove using these objects, like obviously you have to actually prove that they exist and you can utilize them. But then examples of where you can somehow control some ambient geometry, perhaps the most famous ones are Shane Yao's proof of the positive mass theorem for general relativity, the positive mass theorem in relativity, and somewhat related is this Garopp conjecture, which I guess has now been resolved, that similarly to what I said over here about, you've taken manifold, you cross it with S1, you have uniformly valid Ricci. This says that any torus can't admit a metric of positive scalar curvature. So En does not admit metric of positive scalar curvature. So for example, like I said at the start, for n is 2, this just follows from gas point. Okay. So both of these examples were to do with area. Other examples are also similarly to do with area somehow. So a third example, so there's going to be 6 examples. Let's see. We've got a few more to go. So these are perhaps more classical, or maybe people more familiar with the concept of movement surface. There's sort of a, as far as I understand, relatively new sort of technique introduced by Gromov.
So is the second thing now still a conjecture?
No, that's resolved. So there's this sort of new idea, which has been useful in numerous situations, introduced by Gromov, called a mu bubble. And this is kind of like, these things have 0 mean curvature. These are special hypersurfaces with a special sort of, you prescribe the mean curvature in some way. And if you find them again, you find them through some sort of variational method, they're going to also exhibit things like vanishing first variation for a different functional, not just like area, but some sort of prescribing curvature functional. And also, second variation non-negative, which again, there are certain curvature terms which pop up, which you can try and utilize. So these are special types of, I'll say, PMC, prescribing curvature hypersurfaces, which in certain cases you use. And so let me just give you some examples of applications of this. So the first example is maybe sort of more sort of general, which is that they've been very successful in studying sort of global macroscopic properties of three manifolds that have non-negative scalar curvature. So let's say macroscopic properties such as like linear volume growth, stuff like this, of three manifolds with positive scalar curvature. So again, this is a slightly different sort of special substructure you can find in certain cases, which then you can utilize to study the ambient geometry. And another sort of example, which, okay, I include because it's related to what I do or what other work I've done, is that you can use this sort of, let's just say, global properties of minimal surfaces. You can utilize it in this so-called stable Bernstein problem in certain dimensions. So this is being used in R4 and R5. This is joint work with Doug and Curtis Chodosh and Chao Li. So okay, the idea here is that you somehow have some just a complete stable minimal hypersurface in some Euclidean space. And the claim is that in low dimensions it's flat. Okay. And you can utilize these ideas because somehow this is related to positive scalar curvature in some way. So again, yeah, mu bubbles have been pretty useful in studying these problems related to positive scalar curvature. Any questions about anything? I'm just sort of spewing examples.
So there are no purely topological applications. So that's actually for geodesic.
Well, there are. We're getting to that. Yeah, these are more maybe geometric. So my fourth example, okay, this I'm sort of less well versed in, but it's kind of quite interesting when I realized it recently, which is in symplectic topology, you have this notion of J holomorphic curve, which is, okay, maybe this is not the right way to think about it, but it is a surface which is area minimizing because it's calibrated by the symplectic form. So like I said, perhaps this is not the right way to think about it. I don't know. I'm not a symplectic topologist, but these are sort of special two-dimensional area minimizing surfaces. I mean, they're kind of like very loosely like, you take some sort of genus G surface, you take some sort of, it's not quite holomorphic because it's not a complex manifold necessarily, but you take some sort of mapping of that surface into your manifold, which respects the symplectic structure and the almost complex structure on it. These things turn out to be so-called calibrated, which gives it a minimizing, and they've been extremely useful in symplectic topology. So used in symplectic topology. So as far as I'm aware, sort of some applications of this include this Gromov non-squeezing. Theorem about symplectic embeddings of a disk into a cylinder. And you also, I mean, yeah, there's also this invariant you can cook up by counting J-holomorphic curves which pass through some sort of prescribed points, called the Gromov-Witten invariant, which is then some invariant independent of all the choices you made in symplectic structure, almost complex structure. And so you can use to distinguish certain things. So it's also this Gromov-Witten invariant, which uses this notion of J-holomorphic curve in its definition. Okay. So this is my fourth example. Okay. And my fifth example is then manifolds which have special holonomy. Special holonomy, typically you then have, so okay, holonomy, just to sort of remind you, is this idea that somehow you have some, like the structure group of the tangent bundle somehow reduces to a different subgroup of the general linear group. And or in some cases, it gives you a representation of the fundamental group. But, you know, it's all, intuitively, it's just about how tangent vectors change around loops when you parallel transform. So this is sort of related to structure groups. And there's some very sort of, you know, there's this classification of the types of holonomy groups you can have. And it turns out there's not very many of them. And the sort of special ones typically have more structure, and they come with these things called calibrations. And these are special sort of closed differential forms of some degree. That depends on the manifold you're looking at and what holonomy it has. And you know, they have some sort of size assumption. And the tangent planes where you get equality here, so where like the form is really just the tangent plane, you know, somehow if you have a submanifold whose tangent plane is always calibrated by the form, these are very special, and they somehow reflect the structure of the ambient geometry. So yeah, in these cases, so you know, this includes all of, you know, in Kähler geometry, every complex submanifold is calibrated. So you have complex submanifolds. In Kähler geometry, you have these special Lagrangian submanifolds. In Clavier manifolds. And you also get these things called co-associative or associative submanifolds in, for example, if you have a G2 holonomy. There are various sort of special substructures, and all of these things, you know, they turn out to be actually locally area minimizing. This is some famous argument that maybe goes back to Federer. Yeah, it's very simple. And so again, like, I'll comment this on more later, but what's more mysterious, or somewhat mysterious to me at least, is that like, somehow when you're looking at these objects, currently we don't actually really know how to utilize the special structure of these objects to study them. Like their regularity, for example, we only use this information. And this is kind of, at least to me, it's very sort of mysterious as to why we can't, there aren't sort of simpler proofs in these natural geometric settings. You would expect somehow the geometry to maybe help you, but currently we don't really seem to know. Okay, and then, you know, there's all sorts of ideas and conjectures surrounding these objects, you know, potentially how you could come up with invariants to distinguish different manifolds of different, especially like holonomy. So if you have G2 manifolds, there's this idea that somehow you might be able to, maybe it's somewhat analogous to Gromov-Witten, like count certain co-associative manifolds and somehow get an invariant by this count. But this seems to be kind of quite hard, and I'm not sure actually how much progress there's been. And this whole story, you know, this relates also to string theory and mirror symmetry. For example, there's this SYZ conjecture, which is about sort of Calabi-Yau manifold, Calabi-Yau threefolds, and how they could potentially degenerate, and they should degenerate in some special way, which, you know, they're fibered by these special Lagrangian submanifolds. So there's like these objects, again, perhaps not unexpectedly, they should reflect the ambient geometry somehow.
So are you saying there's some general way to define a special submanifold if you have something with special holonomy which specializes in the extreme?
Well, in this case, there's like I say, they're all calibrated by a certain form you have. So these manifolds exhibit a special differential form which satisfies this closed and has this property. And in all of these examples, they're submanifolds whose tangent spaces you get when you act on omega of the tangent space, you get exactly one.
I guess it's to change his question, but why G2 and not another exception?
Oh, I think, yeah, you also get things in other exception in spin 7 as well. Yeah. Yeah, I thought I already had enough example, maybe. Yeah, so let me just say that this is also, there's also a relation here to string theory and mirror symmetry. People are very much interested in these things. Okay, my final examples, I've been going on for like half an hour. Examples is in gauge theory, and in particular, this attempt by sort of sketch of this idea by Donaldson and Thomas to somehow like, yeah, there are sort of basic ideas that gauge theory has been very successful in low dimensions, 1, 2, 3, 4 real dimensions. So somehow you can adapt a form of gauge theory to, say, complex dimensions 1, 2, 3, 4. So, and this is related to these settings of special holonomy. So again, I don't think to be an expert on this or necessarily any of these things, but like, it's kind of interesting how everything sort of fits into the same picture. So this is sort of gauge theory in higher dimensions. Yeah. So yeah, Donaldson proposed this extension of gauge theory, which potentially is useful and can be utilized to manifolds in certain dimensions, but higher than 4, which have these special structures, such as special holonomy, so G2 or Calabi-Yau. And there was very sort of progress on this. So there's this paper by Donaldson and Segal, where they tried to develop some sort of Floer theory for Calabi-Yau threefolds. Again, this sort of the sort of instance here is that, like, you're looking at a Calabi-Yau threefold is the 6-dimensional real manifold. The special Lagrangians are 3-dimensional within them, they're half a dimension. So generically you might hope that the intersection of 2 special Lagrangian submanifolds is a count, it's finite, so you can potentially count it. But then there's all these issues with compactness that come up if this number is finite and if you can actually get a working invariant out of it, which leads to all sort of complications. and somehow it relates to how special Lagrangian submanifolds can degenerate within the ambient space. So, put very broadly, which is where I'll lead, you have these sort of very special area minimizing surfaces or submanifolds, and you're interested in sort of a compactness theory for that, or how you could potentially deal with those manifolds degenerating. And somehow currently we don't seem to be able to really utilize the extra structure we get from these objects, at least from my perhaps naive understanding. And another sort of my last thing, there was this work by Tian, which in attempting to generalize maybe Donaldson's theory from like gauge theory and four manifolds to higher dimensions, what happens is that you take these okay, Donaldson's basic idea is you have this Yang-Mills functional, it takes a connection and takes the L2 norm of the curvature. You look at critical points of this. There are special solutions which satisfy some sort of self-duality called ASD instantons. And then you somehow try to look at all the moduli space of ASD instantons, and you try and compactify it to get some manifold associated to the original one, and then you look at topological invariants such as Euler class of this new manifold. The reason this works is because somehow you can compactify this moduli space in that case. Somehow you get point singularities and you can remove them. When you go up the dimensions, what happens is that compactifying this moduli space is hard, because actually these ASD instantons, they can accumulate energy on a codimension 4 subset. And then so when n is 4, it's just points, and then you can compactify it by removing them. But what Tian noticed was actually that this subset where the energy concentrates is actually a calibrated submanifold in certain cases. So let's just say when compactifying or attempting to the moduli space of anti-self-dual instantons, in certain cases, it's a special holonomy along the situations, this sort of energy concentration or bubbling can occur on codimension 4 calibrated submanifolds. And they have to be calibrated. It's not like that's not bubbling locus is a calibrated submanifold. So bubbling occurs or may occur along a codimension 4 calibrated submanifold. Okay, that's all my examples. So, okay, the point of all of this was to try and convince you that, well, if you want to try and get meaningful invariance in certain situations, so there's two cases here. You can either try and understand the relation between geometry and topology, or how a certain geometric condition influences the overall geometry. Or if you're interested in getting some sort of invariance to distinguish certain manifolds, there are all these problems which, well, a lot of the useful, key ideas at the moment are J-column curves and these special holonomy situations, and this attempt to define these gauge theoretic invariants. These special submanifolds keep cropping up, and in particular, in almost every instance, I think in every instance I've written down here, at least, the special submanifold is somehow related to the area function in some way. So, okay, what I'll talk about for the rest of the talk, which is not too long, is about sort of this picture. So when you want to understand, limits of these objects, you've potentially got sequences of these objects, and you want to try and understand how to, the limit or how to compactify one of these moduli spaces, you're naturally led to having sequences of submanifolds which have potentially area bounds, and that's all the information you have. And so what can you do with this information? You want to get a limit, and you're basically then naturally led to geometric measure theory, which is this idea, which is like in functional analysis, you have solid spaces, maybe you have some control on some energy, Dirichlet energy or something, and then you have some compactness theory, but you have to pass to some weak space. It's the same for geometric measure theory. The energy is area, you have some area bound, and then you can pass to some weak limit, which I'll talk about in a second. So we're naturally led to as far as I'm aware, this is definitely not like the usual way to introduce geometric measure theory. But I think it's interesting, at least here. Okay, I'm sort of just starting to realize that all this stuff's out here, so I'm sort of just getting quite excited, which is why this is a splurge of stuff, which is kind of interesting. So I'm sort of asking myself, okay, so what can geometric measure theory do for these situations?
I'm just a curiosity. I mean, suppose you fix a topological class, okay, in a manifold, and you take an area minimizer that cannot be calibrated, okay? So can you say how big, in a topological sense or some sense, is this class of area minimizing objects that cannot admit a calibration?
Well, I think this is a hard question to ask, because like I think this is kind of like what I'm beginning to maybe think about, which is like, there's this work by Genois, Lou, students, which like, okay, if you have like, if you want to just look at like how bad can a calibrated thing be, or how bad can an area minimizer be, it perhaps it's not too surprising that it can be quite bad, like a priori. But do those bad instances actually come up in the geometric applications? Maybe that's not as clear. Like, if you I guess this is work is being done, so you can't ask me like, do you think this is true or not? Like, it perhaps is not too surprising, maybe in hindsight, that things can get pretty bad. But like in the sort of natural geometric settings where things arise, maybe things are better, or maybe you can utilize things better. I don't know. Maybe other people know more than I do, but it's something which is, there's a degree of arbitrariness in all of this, which, if you just ask me how bad can an area minimizer be, probably quite bad. And I guess now we know that it can be quite bad, as can sort of calibrated things as well. I don't know if that answers. Okay. So, any other questions? Like, I've got like maybe 10 minutes. Took much longer than I thought. So, so maybe I'll just focus on this concept of an area minimizer and what we currently know. So, notice how like in a lot of these examples, like in the calibrated setting, in this J holomorphic curve setting, in this gauge theory setting where things are calibrated, somehow the concept of being calibrated or area minimizing is cropping up an awful lot. So where should I jump to now? So let's focus on area minimizers. And like I said, it's somehow curious to me that like, if I asked you, well, okay, there's this calibrated submanifold cropping up in this situation, how bad can it be? Like, is it like, do you even know that it's smooth about some point? There doesn't seem to be a way, as far as I'm aware, of utilizing the calibrated structure to actually prove such a statement. But instead, the current proofs we know, they say, okay, well, I know it's calibrated, therefore it's area minimizing. And let me just use that information somehow to prove the result. I don't know, it feels maybe somewhat strange that you don't actually utilize any of this special structure, or in specific cases, maybe you know where it comes from. I guess in the setting of J-holomorphic curves, maybe that's slightly different. You do somehow know a priori, you get something which is regular. But yeah, so there's sort of curiosity, if you will, is that the regularity aspect, which is important if you're interested in compactifying stuff or understanding degenerations. So the regularity of these special geometries somehow comes down to only their structure as an area minimizer. So maybe I won't go into detail into precise means what this means to be an area minimizer, but like intuitively, I guess we all know what that means. It's just any sort of replacement. If you have your surface T, say, and you look at something which agrees with T outside some compact set, and on that compact set, you're allowed to replace by anything you want to get a new sort of surface. The area of the new surface is bigger than the original one. So, perhaps like, again, there's a strange way to think about it. Perhaps the simplest sort of type of degeneration you could consider would just be take your area minimizer, look at a singular point, so where you're not smoothly embedded, and just like zoom in. That's a sequence of area minimizers. And what can you say about the limit of this zoom in? So sort of a simple degeneration to consider is T area minimizer X singular point, and look at just sort of loosely T sub rho, which is T minus X divided by rho as rho goes to 0. So shift X to the origin, rescale. And then you're interested in what does this look like as rho goes to 0. So what does look like? So it's somewhat, again, it's a very hard question, so it's not embarrassing, but this is sort of a pretty poorly understood question until relatively recently. But even then, it's still sort of poorly understood in general. So like, okay, just sort of going quickly, there's sort of, you can get some limit out of this because you can prove actually that this has got uniformly bounded mass by this monotonicity formula. So there's a monotonicity formula, which I won't go into. Uniformly bounded mass. So you can get some limit. So get some subsequential limit. But then there's the whole question of, okay, here's some subsequential limit, but okay, but you could potentially have different limits for different sequences of rho going to 0. but is the limit unique? And so, this limit you get, you can prove actually is that it's actually conical, so it's homogeneous, so and it's called a tangent cone. So this is sort of the famous question, like, are tangent cones unique? Okay, and if you're interested in studying, like I say, which perhaps would be very interesting, these sort of compactness properties of these special submanifolds, this is perhaps the simplest limit you could look at. And so, okay, if you can't answer this question, then how on earth are you going to do anything else? So, okay. So maybe we got 5 minutes, I guess. Okay, so maybe let me just write down this theorem then. So, okay, so in this case, for area minimizers, we can actually now, well, I need to say one thing. So, we actually know that these tangent cones objects are actually unique almost everywhere. So, this is like Miller, myself and Anna. So and also it's also by Brummel and Wickramer at the same time. This is last year, that at HM-2 every singular point, I haven't had time to say, but the dimension of the singular set turns out to be n-2. So this is basically saying almost every singular point, the tangent cone is unique. So, okay, broadly speaking, we can understand pretty well this special type of degeneration. However, there's still a caveat that actually we don't understand it everywhere. So there's still a lot of mystery going on here. You also can prove that the whole singular set has some geometric structure itself. So it's not just some horrible arbitrary, like, a bad set that could look like anything. It does have some geometric structure. So you can actually prove that this thing is countably n-2 rectifiable, which it just means that like it's an n-2 C1 submanifold up to some sort of measure 0. So like, and this seems to be the best you sort of hope for in general. But then, like I say, all of this stuff, it really just, we're just using area minimizing. We're not using any, like in these special cases, it doesn't simplify in any way. And it would be rather interesting to actually try and, in these sort of more natural geometric settings, to provide simpler proofs, if that's even possible, to somehow understand what's going on. Okay, I prepared way too much. So, okay, I guess I'll just stop there and see the eclipse. Questions?
When you say limit rule, what's the notion of convergence?
Oh, here it's in like this weak sort of measure theoretic convergence that you use in geometric measure theory. So here, like, I didn't really have much time, but like these things they could be submanifolds, but you give them a structure of a current, which is like, maybe the intuitive way of thinking about it is like you're viewing submanifolds oriented submanifolds. It's just like domains of integration. So like the dual space of differential K forms. So things you can integrate over, and then you're taking like weak limit into in a dual space sense of like, yeah.
Actually is interesting because you could ask the question whether outside of the singularities you're actually converging in a nicer way.
This is true.
So, but it's not completely obvious that you characterize the bad convergence only by the singularities, because you get actually good stuff. But I mean, bad stuff actually converging to something which is not that.
Yeah, exactly. Yeah, like if you take like a complex variety, which fits into this framework because it's kind of by the Kähler form or some product of the Kähler form of itself, like yeah, you can get all these sort of well, maybe not custom, but like branching singularities and things, which when you zoom in, if you will, in this setup, you get like flat, you just get a tangent plane, and so all the singularities are somehow collapsed. But you don't have necessarily like a smooth convergence to this object.
Maybe just a comment when you say that we don't know how to use the special. Maybe you should take the Kähler actually away, because if you, I mean, if you can use complex variables, then of course you will.
Oh, in
that. Yeah.
You mean in like 2D or in general?
In general. Right. I mean, if it is really Kähler, I mean, of course, if it's just like geomorphic, that's a different story. But if it's really Kähler, of course, you can just use classical complex variables theory. Actually.
Oh, sure.
You know, I mean, you're well aware of that. Yes. It's
Yeah,
just like
there are in some special cases, yeah, there are. I guess even in these other instances, like in low dimensional settings, there are also some ways to prove uniqueness of tangent cones and stuff like this. But yeah, I guess in general, make it a bit complex. But yeah.
Okay, if there are no other questions, thanks.